So, welcome back to the class electric vehicle and renewable energy, and in that fundamentals of the battery pack design, that is what we are doing right now. What we have done till now, the fundamental concept of the battery pack, various design which comes as a part of battery pack design, and that four dominant part of that is electrical design, then mechanical design, then thermal design, and the last section which comes as a battery management system, or you can say battery management system and embedded system, it is both together. What we have done in electrical design, that we have designed a battery pack based upon current, voltage and capacity. We took a theory, MPNS theory, that means M parallel and N series. As per our understanding, we always try to go with parallel first and series second. Some of the places where the very large battery packs are there, series first and parallel second also goes, but generally as acceptable rule, acceptable thumb rule, generally it is parallel first and series second. So, what we do with paralleling of cells, we increase the capacity, and after that we put those cells, we consider that as a one unit, and then we put it into series to get the required voltage. Then again, what are other things we have learned in electrical design is, if there is a voltage drop, short circuit scenarios, current parallelization, because it's a difficult to get the required amount of current from the single path, because the current requirements are generally huge in EV application. 50 ampere, 100 ampere, 150 ampere, 200 ampere, like this type of requirement is there. When electronic is concerned, electrical paths are concerned, it's difficult to get such a huge amount of current from the single path. So, what we do, we divide the path so that the currents get divided, and then it becomes easy to design as well as implement the protection. But issues can come if you have not designed it properly. So, this was one of the important part what we discussed there. A part of that also comes into the BMS, which we will discuss during the class today. Then we have gone to the mechanical design. In mechanical design, since we have already designed the battery pack using the electrical design, that's how many cells in parallel, how many cells in series, and then what would be the total number of cells, how that should be assembled. And then we came back to the mechanical design, that okay, now we know how the cells should be arranged in parallel and series configuration. And then we came back to the concept of the modules, cells, modules, and then pack. That's okay. Can we do all the cells in one module? Most of the time, no, unless it is a very small battery pack. So, we have divided those into modules, the number of cells into modules, and then collection of modules become the battery pack. So, based upon the cell, module and the pack requirement, what we found out that what would be the weight of the pack, and based upon the weight of the pack, we started designing the base plate, side plates, tie rods. The another important aspect which came during that time was the pressure, uniformity of pressure on the cell surface, so that during the charge and discharge cycle, the contraction and the expansion of the cell should be within particular limit. If that is not designed properly, what can happen? A cell which can give you a 3000 cycles will be able to give you only 300 cycles, and that's a huge loss, because the battery is expensive and it's an upfront cost. Then we have also considered about vibration, road conditions. Because of the road conditions, the vibration can happen, and that has to be taken care during the mechanical design of the battery pack. We have also discussed about the vibration because of the other parts like motor. If there is any imbalance in motor, and that would certainly be there, it's impossible to have completely 100% balanced motor. So there would be some imbalance. However, that's are generally within the limit, but that will create some vibration, and that would also get transmitted to the battery pack. So one of the ways is that isolate. If you cannot isolate, at least partially isolate, so that your battery pack is always within the limit of the vibration for its reliability. If not, then what can happen? Several things can happen. Your bus bar can fail, your battery casing can fail, and whatever the protection you have used, IP ingress protection, what you have used, may not sustain for a longer time. And that's what all about mechanical design. Then we have come back to the thermal design of a battery pack. What are the things we have done in thermal design? We started from the cell level, and what we have done mostly is to start with the internal resistance of the cell, and that's a very important parameter. And a part of that, for a fixed temperature range and other things, comes from the manufacturer of the cell. To start with, we take that value and calculate the heat load because of the heat generation in the cells, because of the joule heating during the charge as well as the discharge of the battery pack. When we say charge and discharge, that means current flow, and that joule heating is nothing but I square R, and R is the internal resistance of the cell. Now, this internal resistance itself is a function of multiple things like OCV, number of cycles, temperature, and that has to be characterized in the lab during the cell testing itself. So we say it's a cell characterization. That's what we studied in chapter 4. Once we have taken care of, once we know that this would be the heat load or heat generation in the cell, then we also calculate what would be the ambient condition and what would be the heat transfer because of the ambient condition. One of the important thing what we understood there, that the cell does not work very well at higher temperature and it does not work very well at the lower temperature, both sides. So there is a limited range available for a cell to work efficiently. When I say cell, it automatically becomes battery pack. So if cell will work in the limited temperature range, we always try to keep that temperature range, and for that we employ various type of thermal management system, active and passive. And in the passive mostly we use for a smaller battery pack, and that active thermal system generally we use for larger battery packs. Another important aspect of thermal management is that within the pack, we also don't want to have the temperature gradient at a very high level. So we wanted to minimize the temperature gradient. A thumb rule says around 2 to 3 degree temperature gradient is acceptable. In extreme cases, you can go up to 5 degree temperature gradient within the pack. That means from a cell to other cell, if you say to peak temperature, that should not be more than 5 degree. That helps in reduce differential aging because of the differential temperature or because of the temperature gradient there. Then we have also looked upon various electrical current flow paths like bus bar. Then in BMS, that's again there. How can we reduce the heat impact, and if there is a high current flow, what could be the heat, and then how to reduce all those techniques, again using active and passive passive thermal management system we have done. So these all three were the basics, fundamental engineering design. Now the fourth one what we are going to talk about is the BMS design and embed system. it's clubbed two things together. One is the electronic hardware, and the second is the software or firmware which makes it run. So what we discussed today, most of the things is mostly on the functionality, and accordingly what electronics we should select about, and a small part of our software side. That is what we are going to discuss in this particular section. And with that, with this section, we will close this chapter. So let's move ahead. How a battery pack looks like in total. So first we have cell modules, and that is what is the BC as a small is a battery pack. Then we have battery management system. So we have cell modules here. It could be the combination of number of cells. It could be as a module, and it could be a combination of number of modules. So all together, what is kept here will have that bus bar, all sensors included here. Then we have a battery management system. Then we have a pre-charge circuit here. We will discuss in details what pre-charge circuit does. Then we have current sensors in this path, the energy going out. Then we have service disconnect. So either it could be a switch which can disconnect to the battery, or you can disconnect the fuse. So we have a fuse here, you have a fuse here. Sometimes you will have only one fuse, sometimes you will have no fuse also. Then we have a balancing circuit, and that is a part of BMS, that is known as cell balancing circuit. Then we have an insulation monitoring device. When I say insulation monitoring device, for low voltage it does not make much difference, but for high voltage system, where my voltage range is 350 volt DC, 700 volt DC, 800 volt DC, 1100 volt DC. In such cases, those DC currents are very, very harmful for the occupant or passenger or driver. If by any means that is leaking to the chassis, insulation monitoring device detect that and shut off the battery, so that no further current flows into the body, and so that the person who is occupying the vehicle would be in safe condition. So this insulation monitoring device could be a part of BMS, or can be a separate device communicating with the BMS. On and over that, we have a thermal management system. Generally for larger pack, we have wherever we have active thermal management system, and again this could be a part of BMS, generally not, or otherwise it would be communicating with the BMS if it is a separate device. So two separate device, insulation monitoring system and the thermal management system. We will also talk later that what are the architecture of the BMS available. So this is what all about a battery pack. So when I say this, we have discussed all those things in the electrical design, mechanical design, thermal design. We have not discussed much about contractor and pre-charge circuit. We have discussed about thermal management system, but how does it communicate with BMS? We have not discussed. We have not discussed about insulation monitoring device. We have discussed only in, for few seconds that what it does. Will slightly in detail today we will talk about. We have not talked about any preventive or protection circuit much in detail. In this section, we will talk all those things in detail. So why BMS is important? The question comes, why BMS is important? That is not so important for lead acid battery. That is not so important even for NiCad batteries, nickel cadmium batteries. Why it is so important for lithium ion batteries? So lithium ion batteries work best in particular range. So when I say voltage, it for a NMC chemistry, it works best between 2.7 to 4.3 volt most of the time. And in that 2.7 to 4.3 volt, again we restrict that it should not go maybe 3 volt, less than 3 volt, because its life will degrade much faster. it should not go more than 4.2 volt or 4.15 volt to retain its life to the maximum. It doesn't mean it cannot go to 4.3 volt or 4.4 volt, or it cannot go below 2.7 volt. But it works best as temperature is concerned, 15 to 35 degrees C, as voltage is concerned between not less than 2.7 volt, no, not more than 4.3 volt. If it breaches that limit, the cell become unstable most of the time. Several things, temperature shoot up very high, the chemical reactions what is happening inside may be erratic, the insulation barriers between the cathode and anode may fail, that could lead to the internal short circuit. At the lower voltage side, something known as dendrite formation that can happen, and because of that again the insulation what is between cathode and anode can break off. It can go to any voltage, but it's not desirable, it's not meant for that purpose, and it won't cut off automatically. It doesn't have any mechanism. We have to put mechanism, and that's why BMS become important. This is about voltage. The same thing is about current. Now, so cells are meant for obviously a range of current, but then should not exceed some limit, and that's how it is defined as in C rate. Cells are designed for energy storage. Cells are also designed for power delivery. So when I say power delivery or power cells, we say mostly of in that case that can have a huge C rate, but it cannot store a lot of energy. It can still store energy, but not as well as energy storage cell. So when I say energy, the cells meant for energy storage, it can store a great amount of energy, but then it cannot give you the very high C rate. It's limited to 1 C, 1.5 C, maximum 2 C, in extreme cases 3 C. However, a power cell can go up to 5 C, 10 C, 20 C, 50 C. It will give you energy instantly. So each cell has its own characteristic, and if we have, unless we don't work within that characteristic, my protection will fail. My protection will fail means it can behave abruptly in such condition. To keep that cell within the protected limit, we require BMS. Why BMS is important? The first of all is safety purpose. If you see a picture on the right side, a car is burning and has burned to the ashes, and it's nothing but a Tesla vehicle. And why it has happened? Something breached, and it could not isolate itself, and the thermal runaway triggered, and the whole car burned. So for the safety, BMS controls the functional limit of the pack. Whatever functional limit we set based upon the cell characterization, pack, occupant safety, life, cycle life as well as calendar life, whatever we set, whatever we feel that should be through experiments, that we set here. And BMS ensures that nothing goes beyond that set limit. So the BMS controls the functional limit of the pack electrically as well as thermally. It's very important for, it's a critical for accident prevention. Now my pack is designed for 1 C current, nominal 1 C current and peak of 1.5 C current. If somebody try to draw 2 C current, what will happen? So based upon my design, I have designed my thermal system, I have designed my contactors and bus bars. If it goes beyond that, obviously there are some factor of safety, but if it goes beyond that, what will happen? These things will start failing. And when these things will start failing, ultimately it can lead to the fatal accident. And when it can lead to the fatal accident, you will not have much time to save yourself or save the property. So it's a critical for any accident prevention that my limit should never breach. So if I have designed for 1.5 C peak, it should never allow the current to go more than 1.5 C. Either it should shut off or should limit the current. If I have designed my voltage should work between 40 to 60 volt, it should never allow to go above 60 volt, never allow to go below 40 volt. Not always accident happens, not in all the cases, but your life will certainly be compromised. In the sense means battery pack life, and that's again investment, huge investment. So life cycle cost, by maintaining all the parameters in the functional limit, it ensures the pack gives you the maximum life at minimum cost. You cannot reduce the cost of cell, you cannot reduce the cost of pack, but what you can do, you can use the same pack for higher number of cycles, more number of the days, and in that way again you can be able to reduce the overall cost of the pack. It does. How does this all the things happen? How does it limit the functional limit? How do it ensures the pack is running in functional limit? So it keeps on measuring various parameters like voltage, current, temperature. That's the three fundamental parameters always measure. So it keeps on measuring this parameter, and it keeps on doing the calculation based upon the software we have added, firmware we have added, the limits what we have added, and take action whenever anything breaches. Now there comes secondary parameters. What are the fundamental parameters? It's basically voltage, current and temperature. But from the voltage, it's difficult to know how many more kilometers the vehicle will go. So then there is something comes state of the charge, and that becomes secondary parameter that can come from the voltage, charging current, discharging current, all the things together, and then it measures all those parameters and then calculates what is the SOC, state of the charge of the battery. How many more kilometers my vehicle go before discharging completely. So it gives an indication to the driver, I am available only for next 40 kilometers. You should charge, otherwise you will not be able to use it for further kilometers. It helps in preconditioning of the battery. If my temperature is high and if there is an active thermal management system, it can say to active thermal management system, please run, I am very hot. If the temperature is very low, it can say to thermal management system, I am very cold, I will not be able to give you the desired energy or power. I should be at this temperature. So thermal management system runs and brings the battery pack to that level. If over current is being drawn, it says, it sends a message, you are drawing more current, I am not, I will cut off or I will reduce your current. If somebody is still trying to do that by accelerating hard, multiple acceleration, it records those events for warranty purpose. Also, not only for warranty purpose, also for diagnostic purpose, and can be used for identifying the driver behavior. Or if any system in the vehicle is not functioning well and trying to draw more than the required current. So these all the things are being done by measurement and then subsequent calculation within the BMS. So function of a BMS, it has multiple sensors connected to the battery pack, which controls charge, discharge, thermal management, insulation monitoring by using a onboard controller. Now, it can also communicate to outside within the subsystem of the vehicle. That is also possible. So how does it do? First it does cell monitoring. When I say cell monitoring, so it will have a voltage sensor, current sensor, temperature sensor, and with that it keep on checking the cell health, cell condition. Then it does measurement of various things like voltage, current, temperature, pressure, if you have sensors available there. You can also add several other sensors like vibration, accelerometer inside the pack. It will keep on checking the acceleration. Then third is safety. Based upon the cell monitoring or battery pack monitoring using these values, it can check if the battery pack is getting overcharged or over discharged, or a short circuit has happened, or the temperature is very high or very low. It can also measure temperature gradient, polarity. When you are connecting to the vehicle, does any reverse polarity happen? If that will happen, that could lead to the short circuit. So it prevent sending the current or sending the energy during that condition. And what you see here, lithium ion battery pack, you have multiple sensors. Using these sensors, you do the fault diagnosis, and you have also the state estimation like SOC, SOH, state of the health, and the state of the charge. And for fault diagnostic system, you have a fault tolerant control action. If your temperature has shoot up to your the limit what you have set, then it will cut off, and then it will keep on measuring the temperature is coming down below the limit or not. As soon as it come below the limit, it will again allow the current to pass or energy to pass through the battery pack. So that's nothing but fault tolerant control actions. If something is going wrong, it can still work. It sends alarm. So now let's get it repaired. It will not say you get it repaired, but it will give you a code where the problem is. And if you have intelligence in your controller that can detect, okay, this problem said it need to be serviced. Then also it keeps on checking failure modes by sensing all those three things. Yeah, can have multiple other sensors. You can integrate multiple other sensors. Like I said, accelerometer. Like I said, pressure, surface pressure of the cell. All those things can be done here. It also has disconnect battery from the load. Whenever the load is not functional, it will disconnect itself to save the energy, because there is always some amount of current flow, some amount of energy flowing because of inherent resistance of the subsystem. State estimation algorithm, just what we have talked, based upon the sensor's value of voltage, current, temperature, pressure, acceleration. It can calculate state of the charge or state of the health together or independently. Logging and communication. So it keeps on logging critical events, regular sensors value. Either it will store or can send to other systems, subsystems, or outside using CAN and SPI. There are other communications protocol also, but mostly CAN is used for passing on the information or taking the information from other subsystems or even from outside the world using the CAN and IoT. So what are the BMS architecture we have? You can have all the things integrated on the single board, where you have controllers, you have cell balancing circuits, or you have all the sensors, or you can have a slave master configuration, where the slaves will keep on measuring all the values, can also take some preventive or safety shutdown. So you have a redundancy here, and then sends all the data to the controller, which calculate everything and give back the required feedback or control. So here what we have, PMU, MMU and the CMU. This PMU is nothing but pack management unit, maybe master controller. Then we have module, multiple module, that management unit, and then we have a cell monitoring unit. In integrated BMS, all these three things will be together. However, in master and slave BMS configuration or architecture, generally this cell monitoring unit would be independent and will be communicating with the module management unit, and that could be multiple MMUs again, and that would be communicating with the pack management unit. So basically these two types of configuration is being used. What are the BMS application? The core function of BMS, mainly safe operation by measuring temperature, voltage, current, and if you have any other sensors integrated. Then database, all cell parameters, balancing status, all the cells are at the same voltage or not. Input output request, if any requests are coming from the subsystem or anything it is sending out to the subsystem. Then self diagnostics, like self test, everything is within the limit or not, within the functional limit or not. Keeps on monitoring everything by measuring all these values. If there is any error, how to handle it? Then it also does integrity check. When I say integrity check, everything is functional or not. My IMD, if it is a high voltage system, insulation monitoring device is working or not. All functional parameters are within the limit or not. Cell voltages are within the limit or not. So then that's what is integrated. It does by itself. So that's the core BMS function. Then what are the applications? It keeps on measuring SOC, SOH by advanced application like state modeling, prediction, estimation by using the various algorithm. Either you can develop your own algorithm, what's the best algorithm which works best for you. And then we have HD-ROM or EPROM, which keeps on storing whatever data you wanted to store for diagnostic purpose or analytics purpose. Then it has various other control like contactors or relays for connecting and disconnecting the battery pack from the load during the charge as well as during the discharge cycle. Then interface devices, as I discussed in the last, cell monitoring unit, then isolation monitoring, then communication, CAN and serial, and this is done on the real time operating system using the primary MCU, master control unit. In the slave side or a part of this itself can have cell pack monitoring, watchdog, recovery from abnormalities. It will record to maintain the safety, if system is in the safe operating zone or not. And then there is the interface drivers, serial communication, interlock control. If everything is working, then only it will allow the energy to pass on, otherwise it won't. Like my contactor will be on only when IMD says I'm okay, otherwise it won't be on. So that's how is known as interlock control. And for redundancy purpose, you can have a secondary MCU where the minimum required function for safety must be executed even one fails, even one controller fails. In most of the packs, most of the BMS, you have a redundancy control, so that even one fails, others would be able to do minimal application related to safety and protection. It may not be able to do SOC, SOH calculation at that moment, but then it must keep the pack safe, passenger safe, vehicle safe. So what we have is layout and connections. So we have FPGA. FPGA is nothing but field programmable gate array. That means after the manufacturing of that, it's basically a IC, it's a chip, integrated chip, circuit chip. After manufacturing, you can program it, how it should behave, what are the things you want. And then you have input output extension, then BMS electronics, and that comes as a master BMS communicating with the slave BMS, n numbers depending upon your pack size. And these all would be connected with the various sensors like main and pre-charge contactors for controlling and measurement, current and pack volt sensors, power supply and interlock, galvanic isolation monitoring, choose and service disconnect. It can also display locally or to the subsystem or on the vehicle dashboard or connecting with the server to the using IoT. And this N slaves, N module, N cells. So that's how a BMS layout and connections happens in a battery pack. Any question till now?